This is Dr. BDY Sunil, Associate Professor, Mechanical Engineering Department, Institute of Aeronautical Engineering, Hyderabad. In this session, we will be learning about the problems on work energy equation for translation in plane motion and connected bodies. The course outcome of this topic would be calculate the forces resulting in the movement of the connected bodies by using work energy equation involving springs. The topic covered would be problems on work energy equation for translation in plane motion and connected bodies. The topic learning outcome would be understand the principles related to work, energy and power for solving the engineering problems. First, let us see the problem on work done. The problem given is a man wishes to move wooden box of 1 meter cube to a distance of 5 meters with the least amount of work. If the block weighs 1 kilonewton and the coefficient of friction is 0.3, find whether he should tip it or slide it. So this is the problem given, where in first case the object is having weight of 1 kilonewton and the object is being applied with a force horizontally of P with respect to the movement, and the frictional force, as this object is moving towards right side, frictional force will be acting towards left side, and this is the normal reaction N. And in second case, what happens is this same box, it is being tipped in the right and clockwise direction. So while tipping, what is happening is the center of gravity of this object is being raised to a distance of h. Actually, the center of gravity's position is here at the center at a distance of 0.5 meters. But what is happening? For tipping purpose, what we are doing is we are raising this center of gravity, to a height of h. So tipping is making in that fashion, and the direct pushing of the object is with the application of force P onto the object or wooden box. So first we are considering the work done in sliding. In this work done in sliding, we can see the value of N, which is equal to Fu, that is equal to 1 kilonewton, and we have got the coefficient of friction mu is equal to F by N, which will give the value of friction F as 0.3 into 1, that is equal to 0.3 kilonewton. When applied force P is equal to F, that is equal to 0.3 kilonewton, if we calculate work done, it is given as P into S, that is 0.3 into 5, that is equal to 1.5 kilonewton meter, or we can say it as 1.5 kilojoules. Now, when the work done in tipping, in one tipping, the center of gravity of box is to be raised to a height of h is equal to 1 by root 2 minus 0.5, that is equal to 0.207 meters. Therefore, work done in one tipping is equal to W into h. That can be written as 1 into 0.207, that is 0.207 kilojoules. To move a distance of 5 meters, 5 tippings are required. So, overall, therefore, work done for 5 tippings is 5 into 0.207, that gives 1.035 kilojoules. So, with this, we can say that as the low energy is consumed or needed while tipping, the box should be tipped as low energy is needed for tipping. Now, let us do a problem on friction and power. An engine and a train having a load of 300 tons are moving on a straight horizontal track with a uniform speed of 48 km per hour. If the frictional resistance is 68 Newton per ton, calculate the power exerted by the engine if the train moves up a gradient of 1 in 200. What additional power is required to maintain the speed? So, as per the given data, the mass of engine and train is M is equal to 300 tons. So, that gives 300 into 1000 kg. So, weight can be represented as W is equal to 300 into 1000 into 9.81 newtons. And the uniform speed U is given as 48 kilometers per hour. If we convert that into meters per second, we will be obtaining it as 13.34 meters per second. Then the frictional resistance is given as 68 newtons per ton. So total frictional resistance can be obtained as Fr is equal to 68 into 300, that is equal to 20400 newtons. Now consider the case 1 where the force exerted by the train or by the engine is equal to the frictional resistance. If we overcome the frictional resistance, then the object or train will move. So that force exerted can be represented as Fr is equal to 20400 Newton. Then power exerted by the engine, the equation for the power exerted by the engine, that is power is equal to force into velocity. So the value is 20400 into 13.34. So it results in 272136 watts. So it can also be written as 272.136 kilowatt. And in case 2, the gradient of track is 1 in 200. That means for every 1 meter that is going to be increased for 200 meter length, the increase in the inclination would be 1. So sin theta can be obtained as 1 by 200. And the force exerted is obtained as F is equal to Fr plus W sin theta. That is equal to 20400 plus 300 into 1000 into 9.81 into 1 by 200. So this results in 35115 newtons. And power exerted by engine can be obtained as F into U, that is force into velocity. So that gives us as 35115 into 13.34. So the value would be 468434.1 watts. Or we can write it as 468.434 kilowatts. Hence, the additional power required would be 468.434 minus 272.136. So the value additional power required is 196.298 kilowatts. Now let us do another problem on this work energy equation. A small block starts from rest at point A and slides down the inclined plane as shown in figure. What distance along the horizontal plane will it travel before coming to rest? That is the first question. Then the coefficient of kinetic friction between the block and either plane is 0.3. Assume that the initial velocity with which it starts to move along BC is of the same magnitude as that gained in sliding from A to B. So the points given here are A, B and C, and AB is the inclined plane and BC is the horizontal plane. And the inclination is given in terms of sides of the triangle as 3 and 4. If we draw the free body diagram of the first case, here we can observe that as the body is sliding down, the frictional force will be shown in the upward direction and the normal reaction value is shown, and the weight of the object, it will be resolved into mutually perpendicular components. So from this we can write N1 is equal to W cos theta and F1 is equal to mu N, which will give mu W cos theta. And applying work energy principle for this case, R into S is equal to 1 by 2 W by G V square minus U square. When you substitute the values of forces here, minus F1 plus W sin theta into 5. Here there are two forces that are involved in the system. So we are considering the forces minus F1, which is acting in negative direction, plus W sin theta, which is acting in positive direction, into 5 is the distance to which the object is traveling, is equal to 1 by 2 W by G VB square minus 0. Now further simplification, we will be obtaining the value of VB as 5.943 meters per second. Now consider the horizontal plane and the object's movement in horizontal plane. If we take it as N2 is equal to W, the value of F2 would be 0.3 into W, that is equal to 0.3 watts. 0.3 W. Hence, applying work energy equation, R into S is equal to 1 by 2 W by G V square minus U square, we can get the value as minus F2 into S, that is equal to 1 by 2 into W by G VC square minus VB square. And when we substitute all the values given here, we will obtain the distance to which the object moves after sliding down the plane is S is equal to 6 meters. Now let us do a problem on the connected bodies here. Two blocks of A 200 Newton and B 240 Newton are connected as shown in figure. When the motion begins, the block B is 1 meter above the floor. Assuming the pulley to be frictionless and weightless, determine the velocity of block A when the block B touches the floor. And second one, how far the block A will move up the plane. This is the free body diagram of the given system here. We are directly applying two bodies as it is, and the directions in which the forces are acting are being considered. Now for applying work energy equation for case 1, here we are going to get R into S is equal to 1 by 2 W by G, V square minus U square, and substituting the values of the forces that are involved in the system, that is 3 forces involved, minus 200 sine 30 minus F plus 240 into 1 meter is the distance travelled, is equal to 1 by 2 200 by 9.81 V square minus 0 plus 1 by 2 240 by 9.81 V square minus 0. So this summation of the kinetic energy, that is change in kinetic energy, we are applying at a time for the both objects. So first part of this summation is for body 1 and second part of the summation is for body 2. Also, n is equal to 200 cos 30. From the figure we can obtain this. So, F is equal to 0.2 into 200 cos 30, that is equal to 34.64 newtons. Therefore, V is equal to 2.168 meters per second. Now, applying the work energy equation for body A alone, we are going to get minus 200 sine 30 minus F into S is equal to 1 by 2 into 200 by 9.81 into 0 minus V square. So from this, if we simplify this equation, we will be obtaining the value of the distance S as 0.35 meters. Now another problem on this work done. A block of mass 5 kg resting on a 30 degrees inclined plane is released. The block, after travelling a distance of 0.5 meter along the inclined plane, hits a spring of stiffness 15 Newton per centimeter. Find the maximum compression of the spring. Assume coefficient of friction between block and the inclined plane is 0.2. So this is the figure which we can draw from the given data. There is an inclined plane which is inclined at 30 degrees to the horizontal, and the block which is released there from the above, it is traveling 0.5 meters and then it touches the spring. When traveling in this direction and touches the spring here, initial uncompressed distance is like this. After touching or after colliding with the spring contracts to a distance of x here. So this is what given in the figure. Find maximum compression of the spring, assume the coefficient of friction. So from this figure, the free body diagram, we can get the value of F is equal to mu n, that is equal to 0.2 into mg cos 30, which can be obtained as 0.2 into 5 into 9.81 into 0.866, that is equal to 8.495 Newton. And K is equal to 15 Newton per centimeters, that is equal to 1500 Newton per meter. Let X be the compression of spring. Now applying work energy method, we can get mg sin 30 minus F into 0.5 plus X plus minus 1 by 2 Kx square. This minus is taken because the work is done onto the spring, is equal to 1 by 2 into m into V square minus U square. So further simplifying this, we will be obtaining the value of x. Solving the quadratic equation, we will be obtaining the value of x as 0.115 meters. So that is the compression to which the spring will be undergoing. This concludes the session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.